Good afternoon. I think we'll go ahead and get started. I don't want to run too far into lunch. So, my name is David Brown. I'm going to be going over a little bit about threat modeling, and specifically threat modeling in IoT. IoT security is a big thing we hear about a lot. I've listed a couple of these. We don't need to really go through these. There was this thing at DEF CON a couple of years ago, and they found 47 vulnerabilities in 23 different devices. This is during the conference. There's a couple of examples of these attacks against IoT devices that resulted in distributed denial of service attacks, a webcam that somebody could break into and, I guess, monitor your baby. You know, these are kind of, a real interesting one was done on the Jeep Cherokee, and this is a really complicated attack. They got in, they found that the Wi-Fi password wasn't very random. There was about 12 different possible passwords that it could have. That allowed them to get into the network inside of the car through a vulnerability they found in the multimedia computer, and then a problem they found with an MCU that was attached to that bus. They figured out could be upgraded, and it would just accept any firmware they sent to it. So they created some custom firmware for that that basically bridged between that multimedia bus and the CAN bus, and they were able to completely control the vehicle. They had a demo on a YouTube video of you can drive down the guy was driving down the street, and they could apply the brake, shut the engine off, steer. It was kind of scary, actually. The end result is that this is complicated, that when you have a single device, that may not be the whole story. So, a big question is, what is threat modeling? We use the term a lot, but what does it mean? There's a book called Threat Modeling, which seems like it would be a good choice to define this. Unfortunately, the book doesn't actually define what a threat model is, but it does give this list of what are we building, what could go wrong, what should you do about those things that could go wrong, and then basically go back to the first step and do it again. Analyze what you did you do a good job? And then there's about 700 pages in the rest of the book about basically what can go wrong. There's a whole slew of questions you can ask of different kinds of attacks, different ways that somebody could enter, different ways things interact. There's another, I think this is a really good video. These slides will be available. You don't have to remember the URL. It's an MIT computer science lecture on, it's about system security. The first lecture was an introduction that covered threat models. And I really like his definition of this. He says there's three areas that are part of this. There's the policy, which is basically your expected behavior in the system. This is what is and isn't allowed, with the isn't being the hard one to think of. Usually, most engineers, we design systems around what it's supposed to do. And from the security perspective, we tend to have to focus on what it's not supposed to do. Then the threat model is really what can the attacker do? And it's important to think about this because if you take, for example, an attacker who is able to brute force a 256-bit key, there's not much we can do about that. And unfortunately, we don't have that attack right now that we know of. But is your attacker somebody out there who wants to get into your light bulb? Or is your attacker a medium-sized government who has enormous resources? So you have to define what the attacker is able to do. And then lastly is mechanism. What are we going to do about it? What do we implement? From mechanism comes security requirements for the system. There's actually a lot of overlap. They are kind of describing the same thing. The Shostak, the book called Threat Modeling, focuses on the architecture of the system. And Zeldovich focuses on policy and capability. And I found Zeldovich's approach easier to organize and follow, but it's really important to understand the architecture of the system, how everything interacts. So one of the things I discovered is it's really important to focus on a specific application. When you do a threat model, there's a lot of pieces you can talk about. We have a specific network protocol. We have this bus on our system. We've got this software component that does these things. But if you remember the Jeep example, all these things interact. And it's very important to know how all of these things interact together. So we kind of stepped back for what we did on the LITE team to pick some specific examples of what we wanted to do a threat model on. And we basically did this thing. This started out as a sensor, like in a factory. When I then started looking into an actuator, it turns out that the only change is the direction of this arrow. That you can build a system that's pretty similar, so they're kind of the same basic system. I won't spend too much time on this architecture. The idea is, so these purple-ish color are things that are stored in flash on the device. The yellowish color is software. The cloud is up there, so this would be a network interface. This is an SPI bus talking to a sensor. And so the focus of this is on the flow of data through the system, because that's where most of these security issues happen, is where something interfaces with something else. We're going to be producing a threat model document for this. Unfortunately, I don't have it done yet, so I don't have a URL to give you, but it will be available based on this, and it's an enumeration of the threats that go with this. But I wanted today to focus on a couple of specific examples from that of things I thought that aren't quite obvious. So at a high level, if we take a policy that says the data collection host should be able to determine that a given sensor device is valid and only accept data from valid sensors. So I have a bunch of sensors in some environment, say a factory. My host that's collecting that data wants to be able to get data from those sensors and not get data from rogue sensors. We don't want somebody to be able to lie about the sensor data, that kind of thing. So what is the threat? We assume the attacker can generate arbitrary network packets. And you notice we take the worst case view here. Hopefully you do secure your network, that you don't put your sensor network on the internet. But from a security analysis point of view, we'll assume that they've already broken into your network, that they can generate arbitrary network packets. We're going to assume they can't brute force modern crypto algorithms, that you will need to do something else if you're worried about a large government manipulating or accessing your sensor network. And we're going to assume the attacker cannot read from the internal flash on the device, so that most of these embedded embedded MCUs have flash inside the chip, and it's challenging to read that data. So the mechanism for this particular one is we're going to require DTLS with what's called a PSK cipher suite. So that's a pre-shared key. This is pretty common in the IoT space, using DTLS, which is the UDP packet-based version of TLS. It's an adaptation of TLS. So that's an example of one of the 30-some of these I have on my threat analysis. But some thoughts about that, because there's still more questions here. How do we get the secret onto the device? If you look at one protocol that I think covers this pretty thoroughly, the LWM2M, there's a network secret that gets put on each device when it's manufactured. And all the devices in one family have the same network secret. And then that's used to communicate a per device secret over the protocol once the device comes up. you can see some issues there that maybe we could read that. You know, what if that secret gets known? That's a class attack, not a device attack. So there's some problems here, even in these widely used protocols. So if we change one of our threats from attacker cannot read from the device's internal flash to an attacker can read from the device's internal flash, and this is real. There was an exploit, I guess a month or two ago, with one particular device that someone discovered if you pop the top off of the chip and shine UV on it, the JTAG prevention fuse will reverse itself. And now you have a nice JTAG port, and it's real easy to read out of the flash. It's more complicated than that because the device has other protections in it to keep the JTAG debugger from reading the flash, so that they could have debugging support without reading the flash. Until they then discovered that the first thing it does when it boots up is it does a CRC of the flash, of the code contents of the flash. So you set a breakpoint there. Each time you hit the breakpoint, one of the registers has the next byte out of flash. And you just script that, walk through that. No, now you have the flash again. So what happens if we can read that? Well, the attacker can spoof this device, which violates our policy. You now have that device secret, and we can pretend to be that one sensor. Kind of worse than that, if you have the network key, you can act like you're a new device and pretend you're any device on the network, or even a new one. So it's not obvious. I mean, I talked about the fuses and that weird thing with the JTAG. But let's say somebody finds a buffer overflow in one of my network stacks, and by sending a certain packet to it, we can allow reads from arbitrary memory. Then that can be tricked into reading data out of the flash, since it's usually just accessible. So they're not really that obvious, and that's, you have to pick where do we stop this. This is why the end here, the secrets, for example, are important. I'm actually giving a talk on Thursday just about secrets and how hard it is to protect them. So moving on, I wanted to talk about how the policies themselves can interact. Have a policy that says the data collection host should be able to determine that a given sensor device is valid and only accept data from valid sensor devices. And we have another policy that says when the sensor data is available, it should be sent to the data collection host in a timely manner. So this is kind of availability versus spoofability. So not only do we need to prevent attacks, but denial of service is a legitimate thing to consider in a threat model. And you could do something like jam the network. If you have a bunch of wireless devices, put a small transmitter, sneak some little pack of cards sized device into a factory that transmits a jamming signal, that can be a problem. If somebody's on your network, you could send, depending on the protocol, devices that look like they came from one of your network nodes that are invalid in such a way that causes the server to then reject communications from the legitimate devices. So I guess the summary from this is that as you keep diving in, it just gets more and more complicated. Looking at a lower level example, if you look at software update, and caveat is I spent about a year working on MCU boot project, the bootloader, so this one's near and dear to my heart. You have a policy that the device should accept upgrades from the valid upgrade host and run these new versions. And another policy that says the device should only accept upgrades from a valid upgrade host, meaning we don't want just arbitrary people to be able to upgrade their firmware. The threat that we have is the attacker can spoof network from the upgrade host. Generally, this kind of software update is going to be coming from the cloud somewhere. possibly a content distribution network type of service. The attacker can replay old data. So they're watching the network too, and they can send the same packets that were sent before. And then we're going to make the assumption that the attacker cannot break RSA. So if somebody develops large quantum computers, this may not be true. So our mechanism here is to digitally sign the firmware upgrade images with RSA and have a increase-only version number. So if you have version 27 of the firmware, version 26 will not be accepted, version 28 will be. People ask, well, then how do you go back? The point is you don't. If you need to use an older version, you discover a problem and you need to go to an older version, call it 28, rebuild it, and push that out again. I've seen so many complicated mechanisms to, will allow rollbacks within ranges. It's like, just put a bigger number on it. But what happens here with this attacker that can spoof network traffic and is able to replay old data? So we had 25 in our device. The network pushed out version 26, and the attacker just recorded that. Then we go to version 27, and we ignore that. And then a little later, the attacker starts replaying version 26. So I have a firmware update for you. We send version 26 over to the device. So what's it going to do? It's going to get the data. It's going to say, no, this isn't good, and reject it. Then the attacker sends it again. No, this isn't good, and rejects it. And then they do this for half a day, and it drains the battery on your device. Or, because these devices don't have enough RAM to hold the whole flash image, it has to write this image into a working area on the flash, then go back and verify the signature. So if you keep pushing this update for a while, eventually you could wear the flash out. You may get 10,000 writes, and now we have a device that's dead, can't be upgraded, because of this weird little attack of old versions. This is hard. I don't know of a good solution to this one yet. There's things you can do that make it better, that you have to know a little bit more, but it's still pretty easy to just replay it and get back there. So honestly, I don't have a good answer to that one. So conclusions, based on what I've said here. First thing is the model document will be very dynamic. So dynamic it's not ready yet. The difficulty I've had with it is how to organize it. These different models, the different descriptions, give you a different focus and a different order. If you think of it as a spreadsheet, which column do you sort on to even present the data? But from the threat model, that's something we then use to drive development, to decide, well, what's important in our system. Without doing the threat modeling, you could put a lot of effort into something that it turns out doesn't really give you much benefit, and you'd been much better putting your effort in some other topic. And this document is going to grow, especially as we come up with new application areas. For those that were in the previous ARM talk, they talked about some threat models that they'd done, and of course somebody in the audience can think of other applications. I forget the number he said, there's hundreds of different kinds of things that ARM devices are used in, and how do we have to pick specific things and go on. And so, we need feedback in terms of what to build the models around. With that, I guess we got a couple minutes for questions, if anyone has anything. Or crickets. Yes, and we want to use the mics, which should be. What's that?
Everybody's busy trying to solve the last problem.
Right, that may be.
So,
Yes.
are you planning to do the theory of these 30 models or something and do the practical of some of them? So, prove that actually that threat exists and can be executed by a small group of developers, right? So you don't need the medium-sized government for that threat model.
Right.
So I suppose that becomes a priority for lots of people if a threat model can be executed by just one engineer in
Right. As far as practicality, I don't see much reason at the threat modeling stage to try implementing them, except in the case that the model is unconvincing to people. There's an example from the Linux kernel that I think of with that, which was, it was a resource that was allocated, so it was a get without a put in the kernel, which was thought of as, this is a little bug, we should fix that so we don't have a resource leak. And it kind of wasn't until then somebody did that 4 billion times with a small little C program, make it wrap around, then free it. Now it frees something that is still in use. The buffer gets used by something else in the kernel, and they basically made a root exploit out of it. So there are times that you need an exploit in order to show that something is actually serious. That one kind of woke me up to make me realize that, yeah, bugs are usually security problems in software, even when it's not obvious. But, yeah, there isn't a real simple answer to that question. You do need to weigh the attacks, the scope of the attack, the scope of the threat, versus the other aspect of it is, what is the cost of it being exploited? If you think of a light bulb, and you think, well, there's light bulbs. Somebody can fly a drone by my house and turn my lights on and off. Okay, that's interesting. That shows there's a vulnerability, and it's a little annoying to me. But what if your light bulbs are in the stairwell of a high-rise building that people need to leave to exit when there's an emergency? If somebody can fly by and turn off those lights at the inconvenient time, that's now more serious than something that's annoying. So the scope really gets affected by how the specifics of the application.
So the background for my question is that if we say some of the threat models could be quite prolific, then having an implementation of it actually makes a baseline for implementing a test which is generic for people. So people can actually use that implementation. So actually, my implementation doesn't fall flat against this one, at least. So we know that a group of experts have developed some bit of software which proves vulnerability across 5 known devices, that they had those, and then someone actually builds their system and runs these 15 test cases basically, and says that actually we've covered all these bases, and now the only known exploit is where you have basically the, let's say, brute force cryptographic exploit, which we're not going to cover in because there's no value. So that was background to my question.
So to clarify a little more on that, exploits don't usually turn into automated things very well. A lot of times, especially if you talk about things like buffer overflow, it becomes very specific to where did things end up in memory, what's the exact details of it. On the other hand, something that can show there was a buffer overrun is a good test. If you can use a system, there's stack canaries, that kind of thing, compiler features that check for that, that's really useful. Without needing, as long as people believe that, oh, we have a buffer overflow, assume that's exploitable, that kind of thing is good to have tests for, but it's kind of hard to automate exploits. Yeah.
I think you covered the cost of failure But I think the other equally important metric, if you're going to measure metric, because I think a lot of this is going to be trade-off based, is what's the cost to attack?
Right.
And so you have your risk of loss, but what does it cost the attacker to actually execute
Right.
the attack?
And that's why brute force is not generally thought of as a practical attack, because the cost of doing that is so much higher than the cost of failure. So yes, that's a good point.
Except that with machine learning, you're going to be able to do so much more. I mean, it's almost going to be like a race, the quantum race. It's going to be a machine learning race for attacks.
Yeah. I think that's it for time. If we have any more questions, I'll be around though. Thank you.